All right. Good morning, guys. Last time about how we discussed about Gaussian. We said that Gaussian is a computational software that we use to perform quantum ab initio calculations, semi-empirical and molecular mechanics calculation. We made mention that it's a very robust software, and then it has a graphical user interface called Gaussview, and we walked us around some of the functionalities or some of the functions or the operators that we have around one after the other. We modeled for ethylene, a thin molecule. So today we'll be looking at how we can model or how we can model advanced compounds, like compounds aside from ethylene. Ethane is quite very easy for us to model. So we'll be looking at how we can construct. Let's take a look, or we can model for what compound can we look at. Let's take a look at propanone, for instance. How do we model for that? So it's quite a very, you know, the 2D diagram, they usually advise to maybe draw the 2D diagram somewhere. So before you start placing, or you start building in, or you start building the molecules into the working space. Right, we know that propanone has a molecular formula of CH3, C double bond O, and CH3. So we want to work with that. So what I will do is to select this carbon atom, this sp3 carbon atom, since the first carbon that is present in the propanone molecule, the first atom, the first carbon atom that we have is an sp3 hybridized carbon. So we are going to place it here. So we can rotate. Yeah, all right. Then what's now funny is that the second carbon I have is an sp2 carbon, the carbon that is directly bonded to the oxygen. So it's an sp2 carbon. So I will, and what I have here is an sp3 carbon because this carbon is tetrahedral. I come to this display icon where we can see carbon. As we can see now, we can see that carbon has been selected automatically. So we can see there are lots of carbon fragments. You can see the software has been designed to make our affairs such easy, very easy. So we can just come here, take a look at the type of fragment that we want. This is for a triple bond fragment. This is an sp fragment. This is also a divalent, carbon divalent fragment. Now, this is an S single double bond. This is a double fragment. That is a double bond. This is a single to triple bond divalent fragment. So we are the one that is quite in conformity with what we are working with, that is propanone, is this particular one, that is this one that is sp2 hybridized. This carbon that is a single double fragment is what we are going to select, because that is what we will be working with. So we select that. As we can see, it has been selected. Then, like I informed, you don't select this hydrogen. If you select the hydrogen and then you place it here, you see what is going to happen. You can see we don't want this error to happen to us. So let me kindly undo that. So we just select on the carbon atom, and then okay, kind of placed it here. Oh wow, we can see what has happened. The carbon is already attached to the sp3 carbon, carbon 1. The first atom is this carbon, the first carbon atom is already attached to the second carbon atom that has the label 5, C5 on it. This is the second carbon atom. But if we are to number preferentially 1, 2, 3, 4, then number 5 has to be the next carbon atom. Right, so here we still have to deal with something that is quite interesting. We need an oxygen. How do we get the oxygen? We come back to where we have to the builder. Let me go to the builder. If I don't want to do that, then I go to element fragment. But this is the element fragment icon. I can kindly select on that. Look out for the oxygen. I have two ways I can do this. I can either place the oxygen atom there, or I select the double bond. That is, let's look at this. So we can do that in two ways. Either I select this oxygen atom or I just select the other one. It's still falling in place. Let me try the other way around. Let me just go ahead and select back. Sorry. Okay. And then select the oxygen atom. I have it here. Can you see? Still the same thing. So right, either ways, we still have our compound, and mind you, this is not looking like an ketone. This is not looking like a propanone. This is looking like an aldehyde. This is looking like ethanol. That is aldehyde. So we can, and the question is to model propanone. So what do we do? Let's think about it. Then we come back here again, select on the carbon atom, then select the sp3 carbon atom, the carbon that is tetrahedral, and then since the last carbon that is attached is an sp3 hybridized carbon, we place it here, and lo and behold, we have modeled acetone, we have modeled propanone, and our structure is looking all right. So in order to check for maybe the bond angles between each of these guys, let me show you, or let me walk you around how we can do that. So I can just kindly come here. You can see this particular place, this shape where we have, I don't know, yeah, I think that should be the angle. Then I can select, you can see the everything has gone blank because I have to select 1, 2, 3. Now you can see it has translated. This is the bond angle of between these particular three carbon atoms, between this carbon, because this carbon atom has two neighbors. If I want to get a bond angle, I must be between three atoms, at least three. Is it two? At least two atoms, at least two atoms. But yeah, so we can do that. So let's take a look at another. Maybe let's look at it this way: 1, 2, and 3. Let's see what we have. Okay, we can see that's the bond angle here. That's the bond angle here. All right, let's take a look at this 1, 2, 3. What do we have? You can see the bond angle is quite the bond angle is quite funny. Let's take a look at this. All right, we can see what has happened. It's about 109.5. So if I do the same thing for the other ones, the central one I'm selecting is the bond angle for that point. So that's the 109.5, 109.5 degrees. So if I do the same thing here too as well, I'll still get the same thing, 109.5 degrees. So it's quite interesting. Gaussview has a lot of features that we can play around. So this is how we model for simple ethanol. I mean, simple propanone. Now let's take a look at another compound. In order to do that, I can just open a new working space. I click on Ctrl plus N. Then as you can see, you have the icon new on air. So let's say I want to model for something that is quite advanced. Let's say we want to model for, let's say, uh 2 bromo 4 bromobenzaldehyde. How do we model for that? I need a benzene ring. Firstly, I need to put it here because once I can play around that, once I can place in the benzene ring, the problem is already solved. Then what is the next thing to do? I can just come here again. Then I select on the carbon atom, right? Then the double bond, the sp2 carbon. Then I bring it here. Wow, you can see what we have. I can rotate such that I'll be able to place the oxygen atom so that the oxygen atom will be readily available. You can come here, select the oxygen atom here. Yeah, the atom is already on the atom. Then I placed here. I can also come here. That is 4 bromine. I said 4 bromine benzaldehyde. Then you can see the bromine. I place this here. I'll just select ordinary bromine. I can select this. Then wow, we already have a structure. Our structure is already ready for analysis. This is 4 bromo benzaldehyde. You can see we have 14 atoms, 90 electrons, neutral and singlet. This is in the ground. it is still in the ground state. So 1, that is, we take the number or we enumerate the number of atoms we have plus the hydrogen. 6 plus 4, that is 10. Now, then plus 1, 11, 12, 13, the oxygen, and then 14. So it's all balanced. 90 electrons. If we calculate the total number of electrons that we have here, that is 6 times 6, 36. 36 plus another 36, because plus 35. Bromine is 35. That is 71. And then plus, how many hydrogens do we have? 71 plus 16. That is 71, sorry, 71 plus 8, that is 79. 79 plus another 6, 85 plus 1, 86. Then 1, 2, 3, 4, 90. So we all have the electron system is making sense. It is well described, and it is absolutely right. It's absolutely correct. So this is how we model molecules on Gaussview. Perhaps in the next video, we would take a look at how to model big or much more advanced compounds.